Welcome to G Fun Facts Online. Today we are going to change the way you perceive the cosmos. For the entirety of human history, the universe has been a silent movie. When our ancestors looked up at the night sky, they were observing the cosmos strictly through the medium of light. Over thousands of years, we improved our vision. We moved from the naked eye to glass lenses, and eventually to massive radio dishes and space telescopes that could see in X-rays and gamma rays. But despite this technological evolution, we remained deaf. We could see the violent deaths of stars and the swirling hearts of galaxies, but we could not hear the fabric of space itself crashing together. That changed on September 14, 2015. On that day, humanity gained a new sense. We didn't use biological ears, but rather the most sensitive machine ever built by human hands, the Laser Interferometer Gravitational Wave Observatory, or LIGO. For the first time, we detected a signal not made of light, but of gravity. It was a fleeting, oscillating ripple in the curvature of spacetime, caused by the cataclysmic collision of two black holes, 1.3 billion light-years away. In this episode, we are going to explore the monumental science of gravitational waves, moving from the abstract mathematics of Albert Einstein to the practical engineering required to measure displacements smaller than a proton. To really understand what a gravitational wave is, we first have to unlearn the Newtonian view of gravity. Isaac Newton described gravity as a force, an invisible tether that instantaneously connected two masses. If the sun were to vanish suddenly, Newton's equations implied that Earth would immediately fly off into the void. But in 1915, Albert Einstein proposed a radical alternative with his general theory of relativity. He reimagined gravity not as a force, but as geometry. He argued that space and time are fused into a four-dimensional fabric called spacetime. Massive objects like the sun and the Earth curve this fabric, much like a bowling ball resting on a trampoline curves the canvas. Earth does not orbit the sun because of a mysterious tether. It simply follows the straightest possible path, called a geodesic, through the curved environment the sun creates. One specific consequence of this theory was the prediction of gravitational waves. Einstein realized that if a massive object accelerates, it should create disturbances in the curvature of spacetime that propagate outward at the speed of light. Think of a boat moving through a lake. It leaves a wake of water waves behind it. Similarly, two black holes spiraling around each other generate a wake of spacetime ripples. However, Einstein was deeply skeptical that these waves could ever be detected. Space is incredibly stiff. It takes a cataclysmic amount of energy to create even a microscopic ripple. A wave generated by a binary star system would, by the time it reached Earth, distort our planet by less than the width of an atomic nucleus. For decades, the subject was relegated to the fringes of theoretical physics. The first cracks in this skepticism appeared in 1974, when astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar system. These were two neutron stars, city-sized remnants of dead stars, orbiting each other. By timing their radio pulses, they found the stars were spiraling closer together, exactly as predicted if they were losing energy to gravitational waves. This was indirect proof, a smoking gun, but catching the waves directly would require a detector of unimaginable sensitivity. This brings us to the engineering marvel that is LIGO. How do you measure a ripple in space? If a gravitational wave passes through you right now, it stretches space in one direction and squeezes it in the perpendicular direction. The problem is that the wave stretches everything, including any ruler you might use to measure the change. To detect this, scientists turn to the only thing that remains constant in a distorted spacetime, which is the speed of light. LIGO uses a device called a Michelson interferometer. A laser beam is split into two halves. One half travels down a 4-kilometer-long tube, and the other travels down a perpendicular 4-kilometer tube. At the end of each arm, a mirror reflects the light back to the start. When the two beams return, they recombine. The system is calibrated so that the light waves from the two arms cancel each other out, creating destructive interference. In a perfect, quiet state, no light reaches the detector. But when a gravitational wave passes, it distorts the Earth and the detector. One arm is stretched slightly, and the other is squeezed. The light in the stretched arm has to travel a farther distance and takes longer to return. The light in the squeezed arm returns sooner. The two beams are no longer perfectly aligned to cancel each other out. They slip out of phase, and a flicker of light hits the detector. That flicker is the signal. The scale of this challenge is staggering. The change in length LIGO looks for is on the order of 10 to the power of -18 meters. To visualize this, if the arm of the detector were the distance to the nearest star, Proxima Centauri, the change in length would be the width of a human hair. On the actual 4-kilometer scale, they are measuring a change 10,000 times smaller than the nucleus of an atom. To achieve this, the mirrors hang in freefall, suspended by fused silica fibers to isolate them from the vibrating Earth. The vacuum tubes are the second largest vacuum chambers in the world. scientists have to contend with noise from everywhere. A truck driving on a highway miles away, ocean waves crashing on a distant shore, or the thermal vibration of atoms in the mirror coatings can all drown out the signal. LIGO's success is not just in detecting the wave, but in quieting the rest of the world to listen to the whisper of the universe. The signals LIGO detects tell the story of a source's life and death. When two black holes collide, the process occurs in three distinct acts: the inspiral, the merger, and the ringdown. During the inspiral, the black holes orbit each other for millions of years, emitting waves and losing energy, falling closer together and spinning faster. This generates a low hum that rises in pitch and volume, known as a chirp. From the rate of this chirp, astrophysicists can determine the masses of the black holes. Heavier black holes chirp at lower tones, while lighter ones chirp at higher pitches. Then comes the merger. This is the crescendo where the two event horizons touch. In a fraction of a second, the singularities plunge into one another. In the case of the first detection, GW 150,914, two black holes with 36 and 29 times the mass of the Sun collided. The resulting single black hole had a mass of 62 solar masses. Basic arithmetic tells us that 3 solar masses are missing. That mass was converted directly into energy in the form of gravitational waves, following Einstein's equation E equals mc squared. For less than 2/10 of a second, the power output of this single event was greater than the combined light of every star in the observable universe. Finally, there is the ringdown. The newly formed black hole is distorted and lumpy. Like a struck bell, it rings to shed these imperfections, emitting a final dying tone as it settles into a stable state. This allows scientists to test the no-hair theorem, which states that a black hole has no features other than mass, spin, and charge. LIGO has also opened a window onto a hidden population of black holes. Before 2015, we only knew of stellar mass black holes through X-ray binaries, which were relatively light. LIGO revealed heavy stellar black holes, proving they exist, and suggesting they formed in low metallicity environments. Gravitational wave astronomy has also begun to fill the mass gap, the mysterious desert between the heaviest neutron stars and the lightest black holes. In 2019, LIGO detected an event involving a 23 solar mass black hole merging with a 2.6 solar mass object, challenging our models of stellar death. Furthermore, we have found the missing link: intermediate mass black holes. In May 2019, a collision created a 142 solar mass remnant, the first definitive detection of an intermediate mass black hole, likely the result of a hierarchical merger where previous black holes combined to form larger ones. Detecting these signals requires a technique called matched filtering. The sound of a gravitational wave is often buried under mountains of noise, with the strain amplitude smaller than the background vibration of the instrument. To find the signal, data analysts calculate hundreds of thousands of theoretical templates, simulations of what a wave would look like for every possible combination of black hole masses and spins. They slide these templates over the raw data stream. If a section of data mathematically correlates with a template, it produces a spike in the signal-to-noise ratio. This requires immense computing power to account for general relativity's complex equations, including orbital precession and eccentricity. Beyond black holes, gravitational waves are a new ruler for the universe itself, helping to address the Hubble tension. We have conflicting measurements for the expansion rate of the universe depending on whether we look at the cosmic microwave background or local supernovae. Gravitational waves offer a tiebreaker. When binary neutron stars merge, they emit both gravitational waves and light. The waves give us an absolute distance measurement without relying on the cosmic distance ladder, while the light tells us the redshift. This method, using standard sirens, could finally resolve the true age and expansion rate of our cosmos. Looking to the future, we are only scratching the surface. Europe is planning the Einstein Telescope, a third-generation underground observatory with 10-kilometer arms arranged in a triangle. It will be so sensitive it could hear every stellar mass black hole merger in the observable universe. Meanwhile, the European Space Agency and NASA are planning LISA, the Laser Interferometer Space Antenna. LISA will consist of 3 spacecraft flying millions of kilometers apart in space. Unlike Earth-based detectors that hear high-pitched treble waves, LISA will detect the low-frequency bass notes of the universe. It will detect the collisions of supermassive black holes at the centers of galaxies, allowing us to watch the evolution of galactic structures and map spacetime around giant black holes with exquisite precision. In 1609, Galileo Galilei pointed a telescope at the sky and discovered that Jupiter had moons, fundamentally changing our place in the universe. The detection of gravitational waves is our Galileo moment for gravity. We have opened a new ear to the universe. We are no longer limited to light that is blocked by dust or absorbed by gas. Gravity passes through everything, bringing us news from the darkest and most violent corners of reality. We are finally listening to the drums of spacetime, hearing the death spiral of black holes and the tremors of the invisible universe. The silent movie is over. The universe is playing a symphony, and for the first time in history, we are part of the audience. Thanks for listening to G Fun Facts Online.